In the name of Almighty God, I'm Master Sankochi, and today I want to talk about round-jet burning with a syngas combustion. The syngas combustion is the process of burning synthesis gas, a mixture of hydrogen and carbon monoxide, which offers cleaner emissions compared to conventional fuels but faces challenges due to its variable composition and potential. This combustion can achieve lower particulate matter and volatile organic compounds, but the higher temperatures resulting from its hydrogen content can increase emissions. Strategies like lean burning using a specific combustion mode like premier or using dual fuel systems are employed to control emissions and optimize performance. And what are the benefits and drawbacks? The first one is benefits. The first benefit is lower particulate matter and volatile organic compounds. Syngas combustion typically produces fewer particulate and volatile organic compounds or VOCs compared to fossil fuels, particularly when impurities are removed beforehand. Lower carbon monoxide or CO and nitrogen oxides. Studies show that syngas can result in significantly lower uh, carbon monoxide and CO emissions compared to gasoline and natural gas, especially under certain conditions. The next benefit is wide flammability range. The wide flammability range of syngas makes lean burning conditions favorable, which can improve efficiency and reduce emissions. And what are the drawbacks? The first one is high potential. The high hydrogen content in syngas combustion can lead to elevated temperatures, which promotes the formation of thermal and the carbon dioxide emissions is the next drawbacks. While other pollutants may decrease emissions can be higher compared to some conventional fuels depending on the syngas composition and combustion efficiency. The next drawbacks is variable composition. The exact composition of syngas varies depending on the feedstock and production method. For example, gasification of biomass, which can significantly affect combustion characteristics and emissions. And what are the optimization and control strategies? The first one is lean burning. Operating engines in a lean state, high air to fuel ratio is a key strategy to control temperature and reduce the formation. The next one is advanced combustion mode. Research is exploring novel combustion modes such as the premier mode to achieve more efficient and cleaner combustion. The next one is dual fuel operation. In comparison, ignition CI engines using syngas in a dual fuel configuration with a pilot fuel like diesel can improve efficiency and control emissions. The next one is engine controls. Adaptive engine control strategies are necessary to handle the variability in syngas composition and optimize performance and emissions. The next one is emissions control. Specific pollutants like particulates and metallic compounds are often removed before combustion to improve the environmental friendliness of the process. And what are the applications? The first one is heat and power generation. Syngas is used in gas turbines and engines for combined heat and power (CHP) systems. The next application is internal combustion engines. Syngas can be used in both spark ignition and compression ignition or CI engines, either as a replacement for conventional fuel or in dual fuel operation. Syngas is primarily a mixture of carbon monoxide and hydrogen with a smaller amount of carbon dioxide and methane. Its exact composition varies significantly depending on the feedstock and the gasification process, but a typical range is between 30 to 60% or 25 to 30% or 5 to 15% and 0 to 5%. Other components like nitrogen and trace sulfur compounds are also present. And what are the main components? The first one is carbon monoxide, typically the largest component, making up 30 to 60%. The next component is hydrogen, a key component typically ranging from the 25 to 40%. The next component is carbon dioxide, found in smaller quantities, usually between 5 to 15%. And the next one is methane, as a component present in very small amounts from 0 to 5%. Other components is nitrogen, can be present particularly if air is used as a gasifying agent, as is considered a diluent. The next one is sulfur compounds. Small amounts of sulfur containing gases may be present depending on the feedstock. And the next one is water vapor, often present as a variable component. And factors influencing composition. The next one is feedstock. The type of material being gasified, such as coal, biomass, or waste, has a major impact on the resulting syngas composition. The next one is gasification process. The specific technology and operating conditions such as temperature and pressure determine the final gas mixture. The next one is gasifying agent. The substance used to react with the feedstock, for example, air, steam, oxygen, or carbon dioxide, directly influences the ratio of H2O and CO and the overall energy content. A review on fundamental combustion characteristics of syngas mixtures and feasibility in combustion devices. Syngas is a promising alternative fuel due to clean combustion with lower greenhouse gas emission. The multi-component fuel mixture primarily consists of hydrogen, carbon monoxide, nitrogen, carbon dioxide, and traces of moisture. The composition of syngas strongly depends on the feedstock and the choice of production method. The wide compositional variability of syngas poses hurdles in developing applications such as burners and combustion chambers. This review summarizes the recent research on syngas fundamental combustion characteristics such as laminar and turbulent burning velocity, the burning velocity prediction capabilities of various reaction mechanisms were analyzed. Comparing the laminar burning velocity predictions using the different kinetic schemes with available experimental data in the literature establishes the validity of kinetic schemes. Considerable dis- uh, this discrepancy is observed between the experimental data and the present numerical predictions for elevated temperatures at different equivalence ratios. The recent developments in syngas burners, stability regimes, and the need for laminar turbulent burning velocity data at high temperatures and pressure to improve computational modeling of industrial syngas burners are emphasized. The existing research gap in burners to accommodate syngas with the higher mole fraction of hydrogen is also explored. This is a significant increase in demand for energy in both domestic and industrial sectors globally. The gross domestic product or GDP of a country is strongly related to its total energy consumption, which will promote economic development. These findings throw light into the need for optimum energy consumption for the overall development of the country. The report published by the World Energy Council predicts the per capita energy demand will peak before 2030. With an increase in energy demand, the pollutant emissions will also increase, and hence the need for stringent energy policies to protect the environment. Around 78% of global energy consumed is from fossil fuels. The main detriments of the usage of fossil fuels are the contribution to global warming and environmental pollution. The emission norms have become stringent to mitigate the increased level of pollutant emission from various energy generation applications. These norms lead to intense research in the field of clean combustion. And fundamental combustion research is on fast track for finding new generation fuels that emit less or zero greenhouse gases. The Paris Climate Change Agreement urged all countries to reduce CO2 emissions to slow down the global warming substantially. Another crucial point in this agreement was limiting greenhouse gas emissions like CO2 emitted by human activity to a level that trees, soils, and oceans can naturally absorb. And researcher states, given the large fraction of CO2 emissions from coal combustion, 80% between 2000 and 2013, estimates of total emissions are heavily dependent on the emission factors used to assess coal emissions. They also indicate uncertainty of the CO2 emission estimation is high and relative comparison would be appropriate for insights. Few literature supports the argument CO2 emissions from power generation account for 40% by excluding the transportation sector, but a U.S. Department of Energy dataset states globally liquid and solid fuels accounted for 75.1% of the emissions from the fossil fuel burning and cement production in 2014. However, contrasting the datasets and studies are in the absolute quantification of the contribution of fossil fuel to CO2 emissions. All the studies indicate the mole fraction of CO2 in the atmosphere increases at an alarming rate. The primary source of CO2 emission is the usage of coal. One of the best methods to use coal as fuel but with a lesser amount of CO2 emission is the integrated gasification combined cycle or IGCC. With this technology, coal can be converted into synthesis gas or syngas using a high-pressure gasifier. The gasification in IGCC enables the separation of CO2 before combustion, which can be stored through sequestration. Biomass gasification produces syngas, which results in clean and efficient combustion without particulate emissions, rather than burning them directly. Also, the energy extracted from biomass through gasification is a renewable and sustainable energy source. In this aspect, it becomes essential for combustion researchers to have a detailed understanding of the desired considerations of burners and combustors meant for burning syngas to control emissions. During the last decade, the utilization of syngas gained popularity in internal combustion or IC engines and gas burners. The Buchman and researchers conducted a detailed review of the application of syngas in IC engines, and Leuven and researchers and his colleagues analyzed the relevant parameters in the design and development of burners and combustors means to syngas. Syngas and producer gas are multi-component fuel mixtures consisting mainly of hydrogen, carbon monoxide, nitrogen, carbon dioxide, and traces of moisture. Recently, mo- uh, researchers compiled research articles and reported the composition of producer gas syngas generated from the gasification process of various kinds of biomass. 800 different compositions of producer gas along with their mole fraction of H2, CO, CH4, CO2 and N2 present in the producer gas syngas along with their feedstock information indicates that H2 and CO were the dominant combustible species obtained from the different kinds of biomass. Syngas from coal is not renewable. However, syngas obtained from coal gasification and subsequent use in integrated gasification combined cycle or IGC power plants would help in curtailing the CO2 emission in comparison to direct coal combustion. The main challenge is designing efficient burners and combustion chambers is compositional variability, predominantly dependent on the input resources and generation methodology. Continuous variation in the composition of the generated syngas and the producer gas from a given gasification source is another issue. The variation in syngas composition from different gasification methods is shown here. Researchers observed a significant change in the flame structure of the variation in syngas composition at the same equivalence ratio. Designing combustion appliances for such fuels need a fundamental understanding of the combustion characteristics and implications of variations in different fuel constituents. The important combustion characteristics of any premixed combustible mixture at laminar conditions are laminar burning velocity, ignition delay, quenching distance, and flammability limits. And people discuss the information available on the laminar burning velocity and the ignition delay time of syngas. However, the effects of initial temperature and initial pressure on syngas combustion characteristics and turbulent burning velocities were not addressed in detail. This review summarizes the contemporary research on the fundamental combustion characteristics, laminar turbulent burning velocity, and burner technology developments for syngas. An attempt was made to encapsulate the recent development in the measurement of burning velocity of syngas and the design considerations in burner to help researchers and application engineers. The section snippet fundamental combustion characteristics of syngas or H2CO air mixture. The understanding of fundamental combustion characteristics of syngas fuel is vital for efficient utilization in combustion applicants. Most efficient combustion applicants involve substantial turbulence levels, which results in better mixing of gaseous fuel and air before the onset of combustion. And the combustion in many applications is classified as a premixed combustion. One of the critical characteristics that govern the premix combustion process is burning velocity. The burner design of syngas mixture. A burner is a device that is used to burn the fuel with the oxidizer to convert a chemical energy contained in the fuel into thermal energy. The burner can be classified based on the location of the mixing of fuel and oxidizer as a non-aerated burner or nozzle mix burner and aerated burner. Non-aerated burner primarily anchors diffusive flame and aerated burners anchors premixed or partially premixed flame. Some commonly used aerated burners are ribbon burners, radiant plaque. And the conclusion. Syngas is multi-component fuel mixture consisting mainly of hydrogen, carbon monoxide, nitrogen, carbon dioxide, and traces of moisture. The significant difficulty in designing efficient and end-user applications such as burner and combustion chambers is that the composition of syngas varies with the gasification methods. The present study summarizes the recent research on the fundamental combustion characteristics such as laminar burning velocity, turbulent burning velocity, and ignition delay. And what is about analysis of a turbulent round jet based on direct dynamical simulation data at large box and high Reynolds number? The Reynolds number is a dimensionless quantity in fluid dynamics that expresses the ratio of inertial forces to viscous forces within a fluid flow. It helps predict the type of flow, with low numbers indicates the laminar flow and high numbers indicates turbulent flow. The formula is Reynolds is equal to rho VL divided by mu, where rho is density, v is velocity, and L is the characteristic length. and mu is the dynamic viscosity. Flow patterns based on Reynolds number. The value of the Reynolds number helps predict the nature of fluid flow. For example, the first phrase is laminar flow. At lower rainfalls number, the flow is smooth and orderly. In pipes, this is generally when Reynolds is less than 2300 and the turbulent flow phase at high Reynolds numbers, the flow becomes chaotic and irregular in pipes, and this is typically when Reynolds is bigger than 4000. The transitional flow, a region of mixed laminar and turbulent flow, exists between these two ranges, often between Reynolds is larger than 2300 and less than 4000 in pipes. And what are the applications of Reynolds number? The Reynolds number is a critical parameter in various fields of fluid mechanics and engineering, including the first one aeronautic, designing aircraft wings and simulating airflow. The next one is engineering, calculating friction and drag in internal and external flows. The next one is biomedicine, analyzing blood flow in the body. The next one is aerospace, optimizing spacecraft propulsion systems. And the next one is CFD simulation, predicting flow behavior and heat transfer in computational fluid dynamics, or CFD. We have conducted a direct numerical simulation of a turbulent round jet at a previously unattained Reynolds number of Reynolds is equal to 3500 based on the jet diameter d and jet inlet bulk velocity UB in a particularly long box of 75 d. To achieve very fast convergence to self-similarity, we used a turbulent pipe flow at the same Reynolds number and length 5D as the upstream inflow boundary conditions. This indeed results in a very rapid emergence of self-similarity already at very small axial distance z compared to all turbulent jet data published so far, not only for the mean velocities and Reynolds stress as well as the budgets of the Reynolds stress tensor and the turbulent kinetic energy, a nearly perfect classical scaling based on the normalized reduced when no is equal to r divided by z in the range, the z divided by d is equal to 25 minus 65 is shown, but also for the probability density function, or PDF, of the axial velocity used, as well as the associated skewness and kurtosis. All budget terms have been calculated directly, resulting in a marginal error in balance and almost completely Gaussian behavior of the PDF for the axial velocity is observed on the jet axis, while a clear deviation with increasingly heavy tails is evident with increasing distance from the axis. Ramjet flows describe fluid flow ejected from a circular inlet into a semi-infinite domain. At a sufficiently high Reynolds number, this flow becomes turbulent, an important property that goes beyond academic curiosity. In aerospace engineering, turbulent jets play a critical role in jet propulsion systems, where understanding and optimizing jet dynamics is essential to improving engine performance and fuel efficiency. In addition, turbulent round jets serve as test beds for validating turbulence models and simulation techniques, providing benchmarks for assessing the accuracy and reliability of numerical predictions through its unique properties. In particular, turbulent round jet flows exhibit self-similarity in the far field. For example, radial profiles of different statistical quantities can be scaled to converge to a single similarity function. Universal self-similarity for turbulent round jets has long been discussed, where this state should be reached asymptotically and independent of initial conditions. Yet theoretical analysis shows that these self-similar profiles can depend on initial conditions. Experimental results have indicated that although a single jet is self-similar, the profiles differs in various experiments. First assumptions have been inaccurate measurements due to disturbances by temperature or uncontrollable turbulence in the ambient region, which could be regulated by numerical simulations. However, since turbulence around jets grew in the axial direction, numerical simulations are computationally expensive. Therefore, until the 1980, the detailed statistical study of turbulent jet flows relied primarily on experimental methods. And here you can see the simulation by COMSOL and the components that I have used chemistry and transport of concentrated species and also the turbulent flow with coepsilon and coemoga for SPF and heat transfer and also multiphysics is a reacting flow. And you can see the parameter sections that I have defined the inlet volume fraction for CO, CO2, H2O, and N2, and also the geometry for height and width, and particulate and thickness and the diameter, and also jet velocity, which is about 76 meter per second. And you can see as a result here the velocity magnitude, concentration. This is concentration of CO, concentration of CO in three-dimensional, and concentration of oxygen in three-dimensional, concentration of uh, carbon dioxide, and concentration of carbon dioxide in three-dimensional, and also for hydrogen, H2O, and N2. And also you can see the wall resolution. This is the wall resolution, temperature, and the mass fraction. Beyond that, moreover, you can see the plot temperature along the center line. Is also the temperature downstream of the pipe exit and mass fraction along the center line. This is the user that I have talked about about U jet axial velocity downstream of the pipe exit and and so on. Thank you so much for watching my tutorial until the end, and also you can download this simulation from my github.com master script.